Hello. Hello and good afternoon. So today's classes we are going to solve some online session. We are solving some problem and some related to this topic. So before start the presentation, so I will introduce myself. I am Povir Maiti, student from Aijar Mohali. The PMRF ID of my course PMRF ID is 060119889. So I am TA of these courses. The course instructor was Professor Abhijit Vidyash Pandey and course name Polymers Concept Properties Uses and Sustainability. Last few classes we are solved some problem regarding that polymer synthesis, and also we saw some mm, description about the polymer, its processing, and about its mechanical property, about the stress, strain, all of this behavior. So today's classes we are going to solve and discuss something about the polymer, and it's that longevity of the polymer, because the polymers what we are using in environment. So we are mainly focusing on the polymer because of this polymer long life as compared to other material. So we know the polymer have long life, but there will be various effect that can affect the polymer, and that can aging of the polymer, like polymer may degrade, or maybe its performance and its property may be not same as it's as new. So what is aging of polymer? The aging of polymers is refers to the change of properties and performance of polymer material over time a period due to exposure of various environment factors. The polymer aging can be result of combination of chemical, physical and mechanical process, and it can be significantly affect the material's durability and functionality. So when we are talking about the polymer aging, so here the polymer are not dead. So here the polymer, that performance of the polymers what are present in earlier, that may be reduced after a certain time. So what are the factors which can reduce this performance of the polymer? That may be environmental factor. In environment we know there will be various elements are present, like maybe some are moisture are present, so maybe causes some the polymer aging, or maybe in environment the presence of sunlight, oxygen, etc. maybe causes the oxidation and UV radiation of this polymer. So oxidation of polymer, like in a polymer chain, if the polymer are oxidized, then what will happen? So if like you compare this one, your polymer chain, and after initiation your polymer is will be hard dot. So after that, so after degradation polymers on hydrogen liberation, so there will be R dot, and if the oxygen will come, so it will be oxygenate our polymer system, and that may be from like peroxide system or superoxide system, and this peroxide superoxide may degrade the polymer. UV radiations, but you know the UV radiation have the effective energy, or light have the effective energy to radiate to degrade our polymers. So at the UV radiations, if in a polymer there will be saturated bond, like there will be double bond present in your system, in your polymer. So if there will be some double bond present in your polymers, so that can easily UV degraded by the sunlight. So that can affect our polymer. Apart from this, there will be thermal aging. Thermal aging is nothing but when you are applied this polymer in a harsh condition where the temperature is high. So as you know, any reactions and anything will be happen if there will be temperature will be high, that reactivity of this process will be higher, so it will be degrade more faster as compared to the when the temperature is lower. So polymer also shown the thermal aging. Moisture humidity in a polymer system, if there will be some hydrophilic group like some biodegradable polymer or like that, so that can also affect by the moisture and humidity. Chemical exposure, if there will be some chemical environment, like in your system there will be acid base are present, so that can causes the polymer properties and reduce the polymer properties. So chemical exposure, or for the biodegradable polymer by the microbial attack by microorganism that can reduce the polymer properties. So like an example, if the oxygen is calm and it present that peroxide unit here, and after that if you give the light, so this bond will be break, and this bond will break, after this will be continue. So how that process will continue, like polymer degradations, if a step like that, when you heating the polymer, so maybe they are from the radical from the and they are from that initiating radical will be R dot, and this initiating radical after oxygen, so they can from the superoxide, then this superoxide they can from the peroxide bond, and after the termination will be like this, two polymer R dot may be joined together, so they can form a new polymer chain, or they can maybe from the peroxide, and they can maybe break, and they can from that oxide and alcohol. So like this way the polymer can degrade, and lastly we can get the alcohol and some peroxide and oxide system. So if our polymer are degraded by several factors like UV and UV light, oxygenation, all of this. So how we can prevent this aging of the polymer? So we can prevent the this aging of polymer by adding some additives. So incorporating additives like antioxidant or UV stabilizer or anti-aging agent into the polymer formulation can enhance its property. So when we prepare a polymer for the applications, or so some material for the polymeric material, so you can add this the reagent into your polymer system during the processing. So this can enhance the life of our polymer system. That the life means that enhance the properties of the polymer systems, and it can sustain more time as before degradations. So there will be other factor like we can coat it, so to protect our polymer from the UV light, so you can give the protective coating over the polymer. So if you give the effective coating, so that our UV light mm, cannot touch the surface of the polymer, so that can resistance from the UV radiation, moisture or chemical exposure, so that can improve our polymer life. Or we can do like proper storage, so where there will be no sunlight or no environment or no chemical environment are present, so we can storage our polymer in such a there where there will be nothing environmental effect are present, so we can extend the lifespan of the polymer system. Or we can choose some polymer. So what we can do, some polymer have some specific applications, and some polymer, so like if you and like if you when you choose in a polymer like our natural rubber, so you know natural rubber there will be double bond, so that will be more UV degradative. So in place of natural rubber, if you use such a polymer where there will be no double bond system are present, so that can be more effective for this outdoor application. so that the material selection choosing of a polymer which the inherent property can resistance our that such effect like UV and oxidations and environmental effects, so that we can improve the polymer life. Then there will be, we can, how we can the maintenance. So nothing, if we use a polymer system, and these polymers have that lifespan is lower, and if you're doing the protective layer of polymers by coating, so if you maintain this every time, so that can be causes that increase the lifespan of our polymer system. So what are the key factors that contribute to the aging of the polymers? So here we have solved some problem and question answer. So the key factor contribute to the polymers, as you know, they include the environmental conditions. So environmental condition may be like that UV radiations, heat, humidity, oxidation, UV radiation, thermal aging, moisture and humidity, chemical exposure, mechanical stress, and microbial attack, etc. So what is oxidation in polymer aging? So oxidation is a chemical reaction where the oxygen molecule can react into the polymer chain and causing the degradation of the polymers. It can result in a loss of mechanical strength, environment, and changes the polymer properties. So, so during the oxidation, so as I so so this the oxidation can take place into a polymer system, and how they are degrade our polymer. And can polymers age due to mechanical stress? So if you apply the mechanical stress, can this reduce the polymer age? Yes, of course it can reduce, because that repeated mechanical stress can lead to the physical changing in the polymer and resulting in fatigue and micro cracking and reduce the toughness of the polymers. So it can reduce the properties of the polymers after several time or repeated mechanical stress we can apply into the polymer system. So how can one identify the signs of polymer aging? So how we can identify the polymer is aged or not? So the sign of polymer aging may be the color, lose the flexibility, and environment embrittlement or surface cracking, dimensional changes by because maybe that polymers are more elastic behavior when you are newly used polymers, but when you are some age, the polymer elasticity will be lost after several time. So and reduce the mechanical properties, regular inspection and testing can help to identify these signs. Are all polymers equally susceptible to aging? So this will be not right. All polymer not susceptible to equal to aging, because that depends on that what polymers, what molecular structure are present into a polymer system, what chemical compositions are present. So some polymer necessarily more resistant, while the some polymer maybe not. So that depends on the polymer inherent property. What what industries and applications are particularly concerned with the polymer aging? So if you use this polymer system in aerospace or automotive and construction and packaging are particularly concerned with the polymer aging, as they rely on the polymer for various critical applications where the longevity and performance are essential. So when you package some material which are UV protective, and you are packaging a layer, make that your material layer hide from the sunlight, and if your package will be degrade, so that sunlight can then damage your material. So in this application and some like construction where that life of people's matter, or automotive or aerospace engineering, so there we have to must remember and identify the polymer aging, and we have to give a clear inspections regularly. So after that polymers, there will be apart from polymers aging, there will be another factor like polymer viscosity. So polymer viscosity is important when you process the polymer system. So when you process the polymer system, so you have to melt. So what we are do? So polymers to giving us applications. So we have to melted these polymers and giving it to shape to various applications. So giving it melted and how in the melted condition how it behave, that will be depends on the polymer viscosity. So polymer viscosity will be that's which are only essential when your polymer in the processing. So is a measure what is the polymer viscosity? Polymer viscosity is a measure of polymer resistance to flow or deformation under an applied force. It is an essential property in the field of polymer science and plays a significant role in various industrial applications. Viscosity is crucial because the effect of possibility and performance of the polymer's material. Factors affecting the polymer viscosity. So there are several factors affect the polymer viscosity. As you know, when you increase the polymer molecular weight. So as you know that if you an example like ethylene. So if you show the ethylene, so ethylene is a gas, but after polymerization, so ethylene, polyethylene, so polyethylene become a solid. So from monomer gaseous to polymers. So how it certain change gaseous to a solid material. So similarly, with increasing the polymer molecular weight, we have higher the viscosity because longer chains create, polymers are a chains where there will be polymers are like that, there will be entanglement of the chain. So if the chain length will be high, so there will be more entanglement present in the present. So more entanglement means there will be more viscosity. So with increasing the polymer molecular weight, with increasing the viscosity. Temperature, as you know, viscosity generally decreases increasing temperature. High temperature provide more energy. So if you are giving more energy, so the polymers become more. The intermolecular force of attraction will be lower and polymer may easy to flow. Concentration viscosity can increase with higher polymer concentration in a solution or melt. With like when you're giving a polymer like 1 gram polymer in 1 ml solution and 1 gram polymer in 10 ml solution. So if you have 1 gram polymer in 1 ml solution, the concentration will be high. You keep the more viscous and 1 gram polymer where there will be 10 ml solution, so there will be lower viscous. So viscosity here will be lower, viscosity will be here will be high, and here the viscosity will be lower because we reduce the polymer concentration and increase the total volume. So overall viscosity will be lower. Shear rate, viscosity may vary in the shear rate, like shear force is applied. Many polymers exhibit a non-Newtonian behavior, meaning their viscosity changes with shear rate. Units of viscosity may be such as Pascal into second or poise or centipoise depending on the systems or systems of measurement. Generally, the SI unit of Pascal into second are commonly used for the polymer viscosity. So how can we measure the polymer viscosity? There will be several instruments like viscometer, instrument like capillary viscometer or rotational viscometer are used for measure the polymer viscosity. The device apply control the shear force to determine the rate of flow. The rheometer is a rheological testing equipment can provide the more comprehensive data on polymers flow behavior and under various conditions. So what important point about the polymer viscosity? For the processing, polymer viscosity is a critical during polymer processing like extrusion, injection molding, film casting. It affects the case of processing and quality of the final product. So viscosity can affect the processing and also the affect our final product. Because if you lower viscosity, maybe we get the thinner material, or if you higher the viscosity sometimes, or there will be not uniform viscosity in the solution in the melted condition, then we get some product some various defect. So performance in application like coating, adhesives, lubricant, viscosity influence material performance such as separability and film formation. Rheological behavior. Understanding the polymer viscosity rheological behavior helps the engineer and scientist design a material with desired flow property. So how we can manipulate the viscosity? So there we can manipulate the viscosity by adding some additives, maybe additives like plasticizer. So if we add additives like plasticizer, so plasticizers increase the free volume of the polymers. So we are increasing the free volume of the polymer, so the rigid polymer may more flexible and easier to process. Temperature dependent viscosity. The viscosity of the polymers highly dependent on the temperature. So if when you can increase the temperature, so if the melts, the viscosity will be lower. When you solidify, polymer cools and increase the viscosity. And there will be another relation between the viscosity and shear rate. Some polymers exhibit the shear thinning behavior where the viscosity decreases as the shear rate increases. The behavior is many polymer solution and the melts. Here I show that shear stress and shear rate for the Newtonian fluid where the shear stress and shear rate is the continuous example of some Newtonian fluid like alcohol, motor oil, water, gasoline, etc. But our polymer solutions are not like Newtonian type of fluid. It's maybe non-Newtonian type of like soap solution, toothpaste, cosmetic, butter, etc. are the example of non-Newtonian fluid. There will be some Bingham plastics. So after a certain shear stress, the polymers become a Newtonian type. So then we call them as Bingham plastic. The shear thickening. Shear thickening is a such material with increasing the shear rate. With increasing the shear rate, our polymer viscosity will be higher, and shear thinning is a material with increasing the shear rate, our polymer viscosity will be lower. So Newtonian behavior in a Newtonian fluid such as water, simple oil, viscosity remains constant regardless of applied shear rate. The viscosity of Newtonian fluid is described by a single value and it does not change in the increased shear rate. Most polymers do not exhibit purely Newtonian behavior under typical condition. Shear thinning behavior. Many polymers display a shear thinning behavior, which means that their viscosity decreases with the shear rate. With increasing the shear rate, for shear thinning as is shown in the figure, with increasing the shear rate, shear stress decreases. That is, we have the lower viscosity that time. So for shear thinning behavior, where the polymer displays shear thinning behavior, where the polymer's viscosity decreases with the shear rate. At low shear rate, the polymer has a higher apparent viscosity, making it more resistant to flow. As the shear rate increases, the polymer chains experience greater deformations, allowing them to move more freely, resulting in reduced viscosity. Shear thinning behavior is common in polymer melts and solutions and described in applications like polymer processing, injection molding, extrusion because it materials easier to process. The relation between viscosity and shear rate for shear thinning fluid described by a power law exponential. So it is equal to K into shear rate to the power n, where the n are the constant. Shear thickening behavior. Some polymer systems, although less common, exhibit shear thickening behavior. In the shear thickening, fluid viscosity increases, where the viscosity increases with the shear rate, or shear stress increases with increasing the shear rate, as is shown in the figure. For the shear thickening, shear stress is increases with increase the shear rate. The behavior can be caused by phenomena such as particle suspension or polymer chain entanglement. Shear thickening behavior can be material more resistant to flow under high shear rate, which can have advantage in certain applications such a body armor and damping materials. But are polymer systems not as elastic? So it have the two behavior like viscoelastic behavior. The polymers are polymer system can shows that both of the behavior, viscous and elastic behavior, which combine both the viscosity, that is the resistance to flow, and elasticity, ability to return to its original shape. Viscoelastic material can display different response to different time scale of applied stress. For example, they may flow like liquid under long-term stress, but behave elastically under short-term and high-frequency stress. The viscoelastic behavior polymers is often described using complex rheological model and tested with rheometers. So the Markov empirical equation between the polymer intrinsic viscosity and the polymer molecular weight. The equation is written as eta equal to k m to the power a, where the eta is the intrinsic viscosity, k are the rate constant, m is the molecular weight, and the value of k are depend on the polymer solvent systems. For example, a equal to 0.5 indicate theta solvent, and a equal to 0 point typical for the good solvent. So like this and mathematical example we solve. So here what given, if the value of k and a are given, and the Markov equation, in the Markov equation is the k value is 1 into 10 to the minus 2 and a is given 0.5 respectively, that is the average molecular weight. So you have to find out what is the average molecular weight of the polymer whose solution has an intrinsic viscosity of 150 cc is the centimeter cube, so 150 c per gram. So here the intrinsic viscosity, so what are given, so here it is given the intrinsic viscosity eta, which is 150. 150 centimeter cube gram inverse. And also we are given the k value, that is the 1 into 10 to the minus 2 and a value. So now from that Markov equation we know that eta equal to intrinsic viscosity, eta equal to k into m to the power a. So we have to find out the molecular weight, that is the a. So that is the m. So m equal to will be our eta divided by k, and this will be our m to the power a. So if we are multiplying this m to the power a with to the 1 by a, so it will be eta divided by k to the power 1 by a. Now you know the value of eta, which is 150. So 150 divided by 1 into 10 minus 2, and if you put the value, its value of a is 0.5. So 1 by 0.5, then we can calculate the molecular weight of the that polymer. So this is the common example, maybe comes into your GATE exam also. So now we have discussed about the polymer properties like polymer conductivity. So also known as, what is the polymer conductivity? Polymer conductivity, also known as the electrical conductivity or electrical sensitivity, refers to the ability in a polymers of a polymer material to conduct electricity. Unlike the metals, if you compare to the metals, so metal are, we know that, conductive materials, but the polymers are generally insulating material, because the polymer has the single bond, and where the, so any material will be conductive when there will be flow of electrons. So from the single chain, the flow of electrons may not possible easily. So polymers, maximum polymers behave like a insulating material. But in a polymer system, if you increase the some conductivity, like that we have increased the conjugation in the polymer, so then that maybe polymer may be conductive, but not too much conductive as compared to our metal system. So intensely conductive, the most of the polymers have the low conductivity because they have the consist of long chains of covalently bonded atoms. These long chains hinder the flow of electrons, making them insulator. Conducting materials, if we increase the pi conjugated electron systems into a polymer, so that become conductive. Or we can increase the doping. So doping also increase the polymer conductivity. So doping is a process where we can use the foreign molecules or ions introduced in the polymer matrix to increase the electrical conductivity. Common dopants or conductive polymers includes acid, base, and other organic molecules, etc. So application of the conductive materials. So conductive materials may be applied as a sensor, like a gas sensor, where the changes in conductivity can indicate the presence of specific substance. Or we can use in light emitting diodes. Some conductive polymers can emit the light. So the when we are conjugated system, so it will be absorb light, and if you absorb light, so that light will be emit. So when the light will be emit, so that will be give a color. So if they produced colors, so this may be can useful example for the light emitting diodes. Or we can use the conductive polymers using the organic photovoltaic cell, like a solar cell, to capture and conduct electricity generated by the sunlight. So if you compare the conjugated polymers, metals, insulators, semiconductor, so conjugated polymers are comes between that semiconductor region, where the semiconductor has the conductivity range around 10 to the power minus 6 to 10 to the power 2, where the metal have the higher conductivity 10 to the power 2 to 10 to the power 8 ohm centimeter inverse. So if you show the metal have the higher conductivity 10 to the power 6 to 10 to the power 4, while the semiconductor like germanium, indium, etc. as the semiconductor, which is of the conductivity region around 10 to the power 3 2 to 10 to the power minus 6. At the insulator, we have the no conductivity. Also, polymers comes maximum polymer like polyethylene, polypropylene are come into the insulator. We have the conductivity below than 10 to the minus 6. So, some polymers after doping, the conductivity may be enhanced, like polyacetylene. The conductivity may be enhanced to 10 to the power 4. So this will be some conducting polymer like polyacetylene, polypyrrole, polythiophene, polyphenylene sulfide, polyphenylene. So these all are the conductive polymers which have the conductivity into the semiconductor region. So I hope all you understand today's classes. So next class onwards we are going to solve some another problem. So I can repeat once again. So today classes what we are learn about. So first we are learn about the aging of polymer. Then we have for the processing we need the viscosity of the polymer. Then we have use the polymer in insulating material or some polymer as a some semiconducting material. So you know about the electrical property of the polymer. So today's classes we mainly focused on these things. The aging of the polymer. So aging of the polymer may be happened on the various factors like like environmental factor oxidation can increase the uh, polymer degradations and reduce the polymer lifespan. UV radiation also reduce the polymer's lifespan. Thermal aging, moisture, humidity, and microbial attack, etc. can affect our polymer. So what we can do, how the polymer degradation kinetics is going on. If we have an example like polymers, we have where the hydrogen is RH bond is there. So RH bond when you are that heated or UV radiated, so that can produce a free radical, and this free radical uh, absorb some moisture oxygen, and they can produce the superoxide or peroxide bond, and this will be going on, and after that maybe the polymer will be degrade, and polymer made from the alcohol and oxide of the polymer and reduce the lifespan of the polymer. So what we can do the prevention to the aging of the polymer, we can add some additives like UV stabilizer, antioxidant, anti-aging agent, or we can protect this polymer by a protective layer where the UV lights cannot comes into your polymer, or we can store the polymer system in where that there will be no environmental effect are present, or we can use the polymer material such as there will be less chance of the degradation, or we can do the regular inspections or maintenance of our polymeric material. So what are the key factors that contribute of the aging of the polymer? So here the key factor like UV radiation, heat, humidity, UV, thermal aging, moisture, chemical exposure, mechanical stress, microbial attack, etc. What is the oxidation in the polymer aging? Oxidation is the chemical. So it is the chemical changes in the polymer, and polymer are degraded after oxidation. It produces some alcohol and reduce the polymer molecular weight. Can polymer age due to the mechanical stress? Yes, of course, polymer can reduce ages by the mechanical stress and lose its property because the repeated mechanical stress can reduce the polymer properties and reduce the polymer toughness, resulting in fatigue of the polymer. So overall physical property of the polymer are reduced. How we can identify? So identify maybe the polymers will be the surface will be brittle, maybe surface cracking, or maybe the properties will be lower as compared to the new polymer material, or maybe its colors become fade. Are all polymers equally susceptible to aging? No. So that will be depend on the chemical composition of the polymer. So all polymers are not susceptible to the similar aging. So what industries are mainly focusing on the polymer aging or mainly concerned about? So if we use some polymers, so there will be some protective layer, or in the aerospace engineering, polymers are where the higher application performance are needed, so that we have to the longevity and effective performance of the polymers. So then we talk about the polymer viscosity. So polymer viscosity is the about the resistance to flow and how the polymers, because the polymer are the long chains, is not behave like a small molecule, that the small molecule if you are heating, so that can be solid to fluid, but the polymer when you are heating, so polymer become solid to viscous liquid or melted viscous liquid. So with when you have the higher molecular weight, the viscosity of the system will be higher. So if we increase the temperature, so increasing temperature means we are reduce the intermolecular force of attractions. So if I reduce the intermolecular force of attraction, so polymers become easy to flow. So with increasing the temperature, our viscosity will be lower. Concentration also depend on the viscosity. With increasing the concentration, polymer become more viscous. With increasing the solvent volume or reduce the polymer concentration, we can reduce the polymer viscosity. Shear rate. Shear rate also dependent on the viscosity. Some polymers have, with increasing the shear rate, viscosity will be lower for the some polymer, and some polymer cases the shear rate and is continuous with the viscosity, while the other polymer have the, with increasing the shear rate, the viscosity will be increases. So unit of viscosity, more commonly we have used the unit Pascal into second. Viscosity measurement, we can measure the viscosity by viscometer or rheometer. So important points about the viscosity, like processing. So viscosity is mainly about when you process your metal in extrusion, injection molding or film casting. So extrusion, injection molding is when you are apply, like when you are making a polymer solid to polymer bottle, like a thumbs up bottle. So what we have done, so we have to melted this, then we have to give the shape of the polymer. So we have melted this polymer, so we have melted this polymer, like we use this instrument like extrusion or injection molding. Then after we are giving the shape of the polymers to get a bottle like that. So there we need known about the polymer viscosity, and this also viscosity also depend on the performance of the materials what we get. So the uniform viscosity will be maybe good, we get the good products, but when there will be ununiform viscosity, we maybe get the product where there will be some defects are present. The rheological behavior, so overall the viscosity of the polymers are mainly given by its rheological behavior, where we can understand the flow properties of the polymers, and to know the flow properties of the polymers, we can or design our material such a way. So how we can manipulate our polymer viscosity? So we can manipulate our polymer viscosity by adding additives. So adding additives like plasticizer. So plasticizer, what will do? Plasticizer will reduce the rigidity of the polymers by increasing the free volume. So when you reduce the polymer rigidity, so polymer are more flexible, so the polymer viscosity will be lower. Also know the temperature reduce our viscosity. So this will be a plot of shear stress versus shear rate. So this will be giving the viscosity of the polymers. So like a Newtonian fluid, where the increasing the shear rate, shear stress is constant, like our viscosity will be constant with the increasing shear rate, and with the increasing shear rate, our viscosity will be gradually increase. But for some polymers are showing shear thinning behavior. Shear thinning behavior is like that: with increasing shear rate, our polymers viscosity will be lower or shear stress will be lower. But there will be other polymer where with increasing the rate, shear stress will be increased, that is the viscosity will be increased. There will be another polymer like Bingham plastics, where there is certain shear stress, the polymer become Newtonian type of behavior. So there some example of Newtonian fluids like alcohol, motor oil, water, gasoline, etc. Non-Newtonian fluids may be some polymer solution like toothpaste, cosmetic, butter, etc. So Newtonian, then we discuss about the Newtonian behavior where the viscosity are described as single value. It does not change with increasing the shear rate. Most of the polymer exhibit purely Newtonian behavior under a typical condition, but mostly the polymers in the viscous condition are behave as a non-Newtonian type of behavior. So shear thinning polymer. So shear thinning polymer will be like this, where the polymer viscosity will be decreases with increasing shear rate, but for the shear thickening one, with the increasing the shear rate, our polymer viscosity will be increases. Then we talk about the viscous elastic behavior. So like our polymers, it's the combination of the both viscous and elastic behavior. So for the polymers, we have to known about the polymer new properties, which is the viscoelastic behavior, and viscoelastic behavior is the complex as compared to a normal elastic or normal viscous material. So that all depend on our polymer inherent property, also temperature and outer condition also. Then we will talk about Markov equation. Markov equation is the relationship between the intrinsic viscosity and the polymer molecular weight, and equation will be intrinsic viscosity equal to K into m to the power a, where the m is the molecular weight and a is the constant, K and a is the constant. From here maybe some question will be comes if you are given the value of K and a, and we are given the intrinsic viscosity, how we can calculate the polymer molecular weight, or you know the polymer molecular weight, how we can calculate the polymer viscosity. Then we talk about the polymer conductivity. Like we know about polymers are mainly single bond are present, like polyethylene, polypropylene, polystyrene. So that single bond are present, the electron, so you know the conductive materials where the flow of electrons. So for the polymer, the flow of electrons may not possible. So polymer mainly behave as a insulator, but there will be some polymers which are behave as conductive polymers. So conducting polymers come when we giving some pi conjugated system into our polymer system. So when there will be pi conjugated systems, and by doping we have create one electron or hole into the system, and if this will be going on due to the pi conjugation, then our polymer become conductive polymer. So for making polymers as conductive, so you there will be role of some doping material. Doping material may be some foreign molecules, ions etc., that can induces the polymer conductivity. Then we talk about the where they are applied. Maybe they can apply in the sensor, light emitting diodes, organic solar cell, etc. Then the the conjugated polymer may comes into the region of the semiconductor, where the metal with the highly conductive, the conductivity range may be greater than 10 to the power 2. The semiconductive conductor region from the 10 to the minus 6 to 10 to the power 2, where the conjugated polymers comes into this region. Mainly the insulating material where the conductivity is comes is region from 10 below than 10 to the minus 6 are main the more polymer like polyethylene, polypropylene. So those all are comes into the insulating material. PVC all are comes as a insulating material. So thanks for joining. Stop.